Hello friends, welcome to our channel. In today's video, I will be discussing simulation of a three-phase inverter with you. We all know that in simulation of three-phase inverter, we need to connect six switches, like six controlled switches to which we can give the gate pulses. So six different gate pulses can be given to them, and a DC can be converted to three-phase AC with a star or delta connected load. Now, connecting this particular six switches bridge is not a big issue, but based on the pulse which we give to a three-phase inverter or the pulse to each thyristor, on the basis of that pulse, we can have two different parts of the inverter as a 180-degree mode or 120-degree mode. So let's move to a small theoretical aspect of 180-degree mode. So this is a 180-degree mode configuration pulse diagram. So these six pulses, 1, 2, 3, 4, 5, and 6. These are six gate pulses given to the thyristors, whereas we all know the sequence. This is S1, this has to be S2, then S3, S4, S5, and S6. Means first gate pulse will be given to S1, second gate pulse will be given to S2, third gate pulse will be given to S3 and so on up to S6. Now see the pulses given to the thyristor or any switch are conducting for pi, and then from pi to 2 pi they are off. Like they are on for 50% of the duty cycle and then off for another 50%. So as these are conducting for 180 degree, every switch is conducting for 180 degree. According to this, we get a 180-degree mode conduction inverter. Whereas if you want a 120-degree mode, so in 120-degree mode, we will have again six switches, but every switch will be conducting only for 120-degree radians. So you can see this part is up to pi, so 0 to pi and then pi to 2 pi. So every switch is conducting for 120 degree and off for 240 degree. Whereas in 180 degree mode, we were having 180 degree mode conduction and off for next 180 degree. Now the advantage in 180 degree mode is at any instant, let's say between the instant of this 120 degree to 180 degree, we have three switches working every time. So in this first case, see this time S1 is working, S2 is working, S3 is working. If we take this initial instant, then S1 is working, S5 and S6 are working. Let's take any sixth instant where S1, S5, S6 is working. Is at this particular instant, S2, S3, and S4 are working. So likewise, for every 60-degree span, we have three switches working for 180-degree mode. And in 120-degree mode, we have only two switches working at every point of time. Like from 0 to 60, we have S1 and S6. Then 160 to 120, we have S1 and S2 and so on. So for every instance, we have only two switches working and that reflects on the output waveform. So these are your output waveform. The shape-wise output waveform of 180-degree mode and 160-degree mode are almost similar. But if you can see the magnitude, it is Vs by 2 for every magnitude, whereas in 180 degree mode it will be equal to V. So maximum voltage generated will be equal to applied voltage in 180 degree mode, whereas in 120 degree mode it will be half of the voltage. These things we need to understand with the help of MATLAB simulation. Let's move our uh, part to the Simulink window. So for this today's simulation, we will require one switch. So I have taken IGBT slash diode. So you can copy this particular part or you can search in library like IGBT and you can search out. So many parts will opened up which are similar to IGBT. Just see for black colored component as these are required are taken from specialized electrical technology Simulink block. These blue color are related to Simscape. See, if you take your cursor, it will show you the library browser, so from which they belong. So blue components get connected with blue components only, whereas black components get connected with black components only. So this IGBT you can use, or IGBT slash diode also you can use. So both are similar. I have used this IGBT slash diode. So we will require six IGBTs. So I will copy paste first IGBT, and I have connected emitter of first IGBT to the collector of the second IGBT. I will need this kind of three phases. So let's just copy these three things. One more thing, when you drag this IGBT on the Simulink window, you will be able to see four terminals to this. So one is gate, other is collector, emitter, and M. M port shows the measurement port. If you want to see voltage across diode or current flowing through diode, these kind of things can be seen from this measurement port. So you can double click on this particular Simulink and you can uncheck this show measurement port. See, once I uncheck show measurement port and apply, you will be able to see only three terminals. So that's why in my simulation, you can see only three terminals for any diode. Let's connect them in parallel. Now we need to apply a DC source across these parallel branches of the circuit. So let's connect this DC source likewise. I have taken one three-phase RLC parallel load, which can be directly connected to the each leg. So this is first phase, second phase, and third phase. So we will require one voltage measurement also to just see what will be the output voltage. So this is voltage measurement. These two sensors you can use for Simscape components. Now we need to generate pulse blocks. So I have taken one pulse generator block. Let's see what we have filled inside. So in pulse generator block, we need to select time-based simulation as we are working on continuous time. Mostly you use simulation time. If you use external signal, you need to give any step input to pulse generator. Amplitude actually does not vary in MATLAB simulation window. It can be anything, any non-zero value. But in practical world, it happens like every IGBT or any switch requires minimum amount of voltage. So that minimum amount of amplitude to trigger it on is required. But in MATLAB simulation, any value is okay. So one will be helpful. Now, I have taken 0.02 because if you see a diagram for this one, see whatever been the pi to 2 pi mode, based on these gate pulses, you will get the output of the inverter. So output of inverter will be between 0 to 2 pi. So it will be visible as be dependent on your gate pulses. So the duty cycle or time period of the gate pulses will be similar to the time period of the output waveform. So that's why I have taken 0.02. If you want to work on 60 hertz frequency, you can take reciprocal of 60 hertz and place here 0.033. 50% pulse width actually defines 180-degree mode. So see here, 180-degree mode stands for every IGBT is working 50% of the thing. Whereas in 120-degree mode, we won't put here 50% on time. We will put an equivalent portion of 120 degree with respect to the 360 degree. So we will put 33.33%. So here we put 50% duty cycle for 180-degree mode conduction, and for first time period or first pulse generator, the phase delay is 0. Now let's see for the switch 2. So this was our switch 1. This is our switch 2. We need to create a pulse for this switch 2. So as like in the waveform given, switch 2 pulse will be shifted by pi by 3 means 60 degrees. So it will conduct from 60 degree to 240 degree. Accordingly, we need to set the pulse. So amplitude 1 only. Total time period has to be same for all the pulses. Otherwise, your circuit won't work. Again, this will be working for from uh, 60 to 240 means 180-degree conduction mode. So 50% of the time period. Now phase delay we need to vary. So we need to represent 60% degree delay, but that has to be in terms of seconds we need to provide. If it would have been in radians, it would have been in degrees, then we could have directly written 60 here, 60 degrees, but we need to represent 60 degrees in terms of this 0.02. So how much will be 0.02's part when we represent 60 degrees? So 60 divided by or 60 multiplied by 0.02 divided by 360. So this will give you a simplified formula. So you can just put this number now. So for 60 degree, you can take 60. For 120, we will take 120, and accordingly, we will just convert the number. So this 0.02 upon 360 justifies time in seconds per degree, and then we multiplying by degree. So let's apply this. Now let's move to switch 3. So in switch 3, I hope you will be able to recall now what we have done earlier. And here we need a switch 3 to be starting at 120 degree, and it will conduct till 300 degree. See, switch 3 will be starting at 2 pi by 3, and it will conduct up to 300. Okay, so we put 120 degree here. Then S4. After 120, we need to move to next 60 degree. So this will be till 180 degree. Then to the S5. And for last switch, it will start at 300 degree. So this last you can turn on at minus representation of that 300 degrees. So as like this is starting at 300 and continuing till the next part. So see, it is starting at this particular part and you can change that, but this will lead to a first position complete output waveform. So if we start it at this 300 degree, what will happen? Our output will be 50% for first half cycle, and after that we will get a complete output. So let's start it for simplicity point of view at 300. So our circuit is ready. Let's try and simulate it. First of all, I have simulated this particular circuit for 0.1 second, which is nothing but 5 times our time period. So our time period was 0.02. So 5 times 0.02 will be 0.1. So we will be able to see 5 cycles in the scope. So this is our output as like you can see. So let's see this output for 2 cycles and compare it with this window. So see here, it is conducting for 120 degree, then 0 up to 180, again negative 120 for next 120 and 0. So same way we are getting an output. It is conducting for one third half cycle, 120 degree. Then see the output value 100 volts as our input voltage applied is 100 volt, 100 volt output. So the output maximum output in 180 degree mode we are getting as equal to the applied DC voltage. Let's just see what pulses we have connected. So I need to change the settings of scope. We need 6 inputs with 6 layouts. So just check my another video. I have already described how to change the settings of scope and how to save the scopes data in workspace. It will help you. So let's connect all 6 pulses in sequence. So this was our first pulse, second, third pulse, fourth, fifth, and the last. So these are your six pulses. So see, first pulse is starting at 0 and it is continuing till this point. Then the blue one, then the red one. So you can see the pulses, all six different colors up to this paint blue color. So all these six pulses are continuing exactly for 180-degree mode and shifted by 60 degree sparse between each other. And that's what our output voltage was. Now let's move towards 120-degree mode, which won't take more time. We just need to change the duty per period. So for every pulse generator, which was earlier 0.02 with 50% duty cycle, means turn on time was for 0.01 second, but we just want 120-degree mode of conduction. So rather than 180 degree, we need to replace to 120 degree. So earlier we were doing 50% of the time period. Now we need to represent 120 divided by 360. So one third of the portion. So 33.33%. So this change only we need to do in every pulse generator. Rest things are same. So see, this is our output waveform for 120-degree mode conduction. And this is what given in your 120-degree mode conduction. So the maximum output will vary. See here, we are getting one pulse at 50% and another pulse at 100. So this is called cruciform waveform. If we have pure resistive load, we won't be able to see this particular track. So we can change to resistive load by making a power, or let's say 50 hertz and active power 100, reactive power 0, capacitive power 0. Let's try to simulate this resistive load. So see here, this justifies your sinusoidal waveform. So when you can connect the filters at out terminal, you will be able to see a clear sinusoidal waveform. So I hope you will be able to get a clear idea between 120-degree mode conduction and 180-degree mode conduction. Of course, the output values varies a lot, and I hope you might have got all the aspects regarding simulation and understanding of the 120 and 180-degree mode conduction. Thank you for watching this video. Please like, share, and subscribe.